Also, since we'll be using TensorFlow with a quite large data set, our recommendation is to run it on Colab. So you may have like a K80 free from Google. So yeah, better than the CPU of your laptop probably. Yeah, you can find the EuroSciPy.ipynb, which is in the root folder of the repository. And if you open it, even on GitHub, you will find that there is a link to Colab. If you open the link to Colab, then it should probably work out of the box. You just have to make sure that you are running a GPU instance, and in order to do it, you go on Colab, and there is like the, if I remember correctly, like the session menu tab. You open the session menu tab, and then you can you open the, okay, thank you. It's the runtime, sorry. You click on runtime, you go and do change runtime type, and then you can specify whether you want Python 2 or Python 3. The tutorial will be using Python 3, and also the hardware accelerator, whether you want the GPU or you do not want any form of accelerator. And also we are recommending you to also execute the first line of the cell that you're gonna find on Colab. So you have already the downloaded data set, and you can follow us when we do the stuff. Also, there is a cell which will link you to a TensorBoard. Using TensorBoard with Colab is still a bit of a pain. But using this workaround, we basically give you an ngrok version. So you can open it and check, for instance, the graph or the image that are generated. It should be like a unique static site, basically. If you have an error in the import section, there may be, some of you, depending when you open the Colab, there may be an import line called import TensorBoard Colab. You want to delete that line because it doesn't do anything. It will give you an error saying that you do not have the packages, and it's okay, you don't need the package anymore. Yes? Okay, open the IPython notebook, which is this one, EuroSciPy. When you open it, even on GitLab, you will see that there is that link. If you click on View in Colab and you do open in another, like in another tab or in another window, I don't know what you prefer, then like show it them. It brings you here. Then you are logged in. Colab basically works as Google Drive stuff. So if you have a Google account, you can use it. It's free of charge, so it's okay. If you don't want to like use it because you don't want to use Google and stuff like that, then you are free to follow around as you prefer. This is just a nice way because they give you a free K80. Which is actually, it's not a real true K80. It's quite slower than the real one, but it's still faster than any CPU you may use. So, yeah. For instance, if you have like, I don't know, maybe you have like some gaming CPU, gaming laptop and stuff like that, maybe it's better if you use your laptop in that case. But if you have any decent CPU, any decent GPU. And you can find the two requirement file if you want to run it locally. There is one which is the no GPU version and the one which is the GPU version. The only difference it is that one uses TensorFlow-GPU and one uses normal TensorFlow. So it depends on whether you want to have the one with, for instance, CUDA and stuff like that. Okay, we'll be starting in a couple of minutes. If you have any question for the setup, please ask it now, because we won't be going over it when the talk starts, because we are assuming that you have already everything working on your system.
Sorry, what's the link for the collab?
The link it is in the first cell of the EuroSciPy 2018 IPython notebook. Okay. It's the first link. This one, viewing collaboratory. Okay, if you see, this one is your link to TensorBoard. When you execute the cell, it will make you this ngrok link. And if you click on it, it will bring you to your TensorBoard session. So you can watch your graph and you can watch the train. Yeah, but as I told you, it's pretty slow. So yeah, don't really know if you want to see it. We probably have already some images generated, but they are not that good. Because we are we are in the still few epochs of training. So, but we will be uploading a proper GIF showing you some cool output in the following days when we go back to the office and we run the model on our machine properly. So we log the stuff. Just some last information. We will be having a question time at the end of the talk if we manage, because it's quite a lot of stuff to cover. We will try to cover it all. Otherwise, of course, you can just try the notebook for yourself. They are pretty much more clear than we may be. And especially the last part, which is the one where we show you how to put the model in production. It's not, of course, how we put the model in production. It's a simplified way. Basically, it's just a bunch of bash command. In order to try it out, you have to have a Google Cloud account, because we are using Google Cloud machine learning engine. So if you don't have it, it's no problem. You may be able to try it also with, for instance, I don't know, Amazon SageMaker or any other solution that you may want to use. The only thing is that if you need to do the last part, you may want to use your Google Cloud account and do all the step to authorize your Google Cloud SDK on Collab. But if you, otherwise we are gonna just show you the steps, which are really, really simple. And since it's 14, we are gonna start. So,
hi everyone. So just a few words about us. We are Paolo Galeone and Michele De Simoni. We are working for Zurotech. And we have to say thanks to them for making this talk possible. And in this tutorial, we are going to show you pretty much everything from the basic of GANs on to how to develop the model in production. So since everyone here should just already have the proper local setup or the Collab account, we can just start with the first notebook. It's in this folder.
Just one thing, the first few notebooks, basically like Paolo's part, it is not on the Colab, but you don't need to have the Colab to follow it, because it won't be doing any computation heavy stuff, so you can just follow it from the notebook. My part, which is the more like practical one, will be the one that is already present, the code is already present on Colab, and the Colab code is just a copy and paste of the code that you can find on your notebook.
Do we have to run the EuroSciPy 2019 notebook?
Not for this part. Like for Paolo's part, you don't need to run anything. You can just follow along using the notebook that are already on the site. For my part, I will tell you what to do, and there is no exercise. You can, if you want to run it, you can run it. So you can have like, I don't know, like see the computation for yourself. Otherwise, we will be simply going over the various steps, because the process of training the GAN is quite time intensive and cannot be fit, of course, into a 1.5 tutorial. So.
I already got an error on Colab.
Yeah, I'm gonna let Paolo talk, and I'm gonna going over to you and see if anyone has some error.
Okay, so we can start from the theory of GANs. And this is a table of contents. So in very few time, I'm going to introduce you just the intuitive idea behind the adversarial training. That is pretty much exciting, because it's revolutionized the computer vision fields in particular. But our GANs are a generative model. And we can also say that the most important part is how GANs are trained. The process of adversarial training is something that has never seen in the machine learning arena since the introduction of this idea. And it works basically in this way. We have two models. One is the generator, whose aim is to learn how to map from a prior noise distribution, here noted with PZ, how to generate samples that will be, let's say, pretty much like the real samples that will came from a real data distributions, and as judged by the discriminator. In particular, the value function is described like a min-max game, in which we have the generator that wants to minimize this log probability. As we can see here, the generator takes as input a random vector of noise, just random values. And the discriminator must judge which is the probability of these samples of being real or being sampled from the real data distribution. So as you can see here, we have the. Pardon? Oh. Yeah. Does it work? Okay. Okay, perfect. Okay, so yeah. The min-max game that these two models are going to play is just the discriminator that must judge if his input is data coming from the real data distribution, or if it's generated data coming from the generator network. We won't dig so much in this mathematical explanation, but what it's really important here is the intuitive idea. The idea is just that we have two different networks. They are competing one against each other in order to, one, generate samples that can fool the discriminator, and the other to not being fooled by this generator. As you can see here, in the original formulation of the GAN min-max value function, we have the second term, that's the term that the generator will try to optimize, that can have some problems. Just for instance, if the discriminator outputs 1, we have the log of 0. And of course, if the discriminator outputs 0, we have another constant values that's the logarithm of 1, that's 0. And this can be a problem, in particular when we are in the early steps of training, because the generator can easily find if the input is something garbage, because the generator is not still able to generate something meaningful. And therefore, Ian Goodfellow itself, that's the creator of the GAN, suggested to use a non-saturating value function that just replace these saturating terms with the log probability of the discriminator, but instead of minimizing this probability, we are going to maximize. And mathematically speaking, it is just the same. So the real power of GANs is that both G and D can be any type of neural network. So in particular, depending on the data type you are going to use, you can just define a different type of networks. For instance, if you are going to work with images, the standard de facto for working with images are convolutional neural networks. But instead, if you are just working with scalars, you can just work with some fully connected networks to make both the generator and discriminator. And yeah, of course, it's heavily data dependent, and so it's one of the thousands of hyperparameters we have to take in account when we define GANs. The training phase, that's the adversarial training. It's simply what we just want to do is to sample a certain number, m in this case, of noise samples from the prior noise distribution. Then sample other real data from the same number of samples from the real data distribution. And then we can just train the discriminator using stochastic gradient descent and making ascending this gradient. And for the generator is the same. Just remember that we are using the non-saturating loss function. Therefore, what we are going to do here is to just take m samples of noise from the noise prior distribution, and then feed it to the generator, use the discriminator to make it judge the quality of the samples generated by the generator, and then ascending the stochastic gradient descent. This is just the intuitive idea, and fortunately we will show you how to implement this with TensorFlow, and we don't have to take into account more or less any mathematical detail like this. We just have to define the loss functions and how this two network interacts, and let TensorFlow work for us. Of course, this value function is the original value function introduced by Ian Goodfellow and is unconditional GAN. What does it mean? This means that both x, the samples sampled from the real data distribution, and the noise vectors have no constraints. Instead, there's another paper that introduced the conditional GANs, and the conditional GANs just add a condition to this probability distribution. In particular, when we are going to sample data from the real data distribution, we can, for instance, sample a value x, knowing that the feature y is true. For instance, you can sample an image with drawn a cat and assign to this image the label cat. And we have to do the same from the generator of the input, just we concat the label to the input noise vector. And that's pretty much all the theory needed for have an intuitive idea of how GANs works. So we can just see what does unconditional GAN can do. This is a classical example. This is a GAN that is generating digits. This is a GAN trained on the MNIST dataset, and yeah, that's all. And instead, what we can do when we condition a GAN, we can force the generator to generate samples that are within a particular class. For instance, the first row here are samples generated by a GAN trained with input the label 0, and so on for every other numbers. These numbers are not real. These numbers are generated by our generator. And with conditional GANs, we can do something that's really impressive. In particular, in computer vision, there are tasks that are before GANs were simply impossible. For instance, this one is terrific. We can just give an input to this GAN as a condition, this sketch of edges, and this is the output of our GAN. And this is pretty much incredible. So this is just an overview of the theory, and now we can go to the other notebook here on chapter 2 and try to write a simple GAN from scratch using TensorFlow with the old API. I say old API because right now in TensorFlow as the TensorFlow team added the tf.estimator API and the tf.data API that are an high-level APIs that will simplify the definition and the training process of the model. But instead, in order to understand how GANs works, it's somehow better to write GANs from scratch. And there's something we should know about TensorFlow. In particular, there's something about the naming of the variables we should take in account. So with TensorFlow, we first we divide the definition of a computational graph and its execution. And when we define a computational graph, of course, every variable and every node has a name. And this name, of course, if it's under a scope, can be equal. For instance, in this example, the name leaf1 and leaf2 should be different because it's not possible to have the same variables defined 2 times under the same scope. I just said these things to you because in a few minutes we are going to write the discriminator, and the discriminator is going to be fed with real and fake samples. In order to not create something ugly to see and to use, we are going to use this feature of the variable scope method of TensorFlow that will allow us to define the network once and share the network's parameter. And so we will define the network, giving a random giving the generated samples as input, and then we reuse the same network to feed again the discriminator with the real values. So what does a GAN learn? The aim of the generator is, of course, to learn data distribution. As an example, we are going to create a GAN that will learn this data distribution, a Gaussian with a mean of 10 and a standard deviation of 0.1. So this is our target distribution, and we are going to sample the data. Of course, we need right now to execute these lines. And in order to make TensorFlow works, there's another thing we have to take into account, is that since TensorFlow splits the graph definition and the graph execution, this split is made using the session. Before defining the graph, we just live in another world. Then when we want to run the computational graph, we place this graph into a section, and the section itself lives on a physical device. So right now we are going to instantiate a session, and that's pretty much Sorry, because I already ran this notebook, so there's just a session attached to this notebook, but it works. So right now, what we're going to do is to just generate our target distribution. So we use TensorFlow itself to generate the samples. We are going to use the random normal with mean 10 and the standard deviation of 0.1. And we just run this code, and as you can see, we plotted the histogram, and this is our target distribution. And right now, we are going to define both the generator and the discriminator networks. The generator should just have as input a batch of noise. We can arbitrarily define the shape and the size of the latent space we are going to sample in order to give the generator the correct input. And also is completely arbitrary also the definition of the network architectures. So since we are working with scalar values, one standard architecture is just a fully connected neural network. And so our generator will take in input something that right now is just a variable input. And we will create just some two fully connected layers. And the output, of course, should have the same size of the real data distribution. So in this case, the number of output units is 1 because we are going to generate samples, scalar samples. The discriminator instead takes as input a variable input, and also have this reuse parameter, as I explained above. And in this case, we just define our discriminator as a fully connected neural network with 32 hidden units, activation function that is the ELO, but you can use whatever input function you want. It's just another input, is just another hyperparameter we have to try. And in order to see which one is the best for our training dataset. However, also in this case, the discriminator should output the probability of an input samples to be generated, so real or fake. And so this is just one output unit, and that's all. As you can see, even if we are going to use the discriminator output as a probability value, there is no activation function here that, for instance, a sigmoid would have squashed our values in 0 and 1. But this is required because we are using TensorFlow, and we are using the predefined loss function of TensorFlow that will apply the sigmoid to these values in order to consider the output of the discriminator a probability.
Can I ask a question? So for the generator, the graph that is being built, why is G connected to FC1? You might have explained that. I missed it if you did.
Because this is a typo. Yeah, of course, this one should be FC2.
Okay.
Yeah. Thank you. Okay, so we can run this one. Okay, right now we can just define our networks. We have defined the function that will define our computational graphs, and we can define the input for both our networks. Our discriminator, of course, will take an input placeholder. A placeholder in TensorFlow is just a way to say, hey, when this graph will be executed, somehow someone from the outside should feed a value that has unknown size in this dimension. That means a batch of any size of values with one dimension, so scalar values. So our discriminator right now just take this placeholder in input, and this is the output neuron of our discriminator. We are going to do the same for the generator. Exactly, we just defined that our prior noise distribution are a vector of 100 random values. And we define the generator, and right now we are going to use the reuse flag of the variable scope function in order to define again the discriminator
but without redefining the variables. We are going to share the variables previously defined here, but this time using the input, the generator, so the fake samples. This is the output of the generator, so the fake samples are pasted as input to the discriminator, and the fake is just the discriminator result when the input is fake. So the loss function, that's the way to connect the generator and the discriminator networks. As I told you above, the output of our models are linear neurons, because we are going to use this loss function that are integrated into TensorFlow, and they will apply the sigmoid for us. So our discriminator loss function, since it is to just discriminate between real and true samples, will be the sum of two binary cross entropy. And this is the loss that we are going to define in particular with this just two lines. As you can see, the discriminator loss for the real samples is just the mean, as you can see for this part. Reduce mean just computes the mean of the sigmoid cross entropy with logits, that's the binary cross entropy. With logits is the unscaled logits, so the linear output neuron in which we apply the sigmoid. And the labels, we are going to say that the real samples are going to be labeled with ones, while the fake values, it's the same exact formula, but instead we are going to label them with zeros. The generator loss function instead is exactly the same as above, is just this part. And as you can see, we are going to reuse the binary cross entropy. So we are going to ascend this gradient. There's a minus sign here and here, here. This is a gradient ascent. And pretty much that's everything we need to do to define a model, define the loss functions. So what just we need to do is to define the real adversarial training part.
So is this all set up? Everything before this was set up?
This is just the model definition and the loss definition.
Okay. So there was on the first where you define D-real, the comment says a batch of values sampled from the real data.
Yeah.
I'm having trouble seeing where Z is being used for sampling from the real data. Or is this just saying that this is the placeholder where the data is going to be input? We're not actually sampling the data yet.
Yeah. We are going to do this when we place the.
We're going to do this later. So
yeah.
This is all just set up.
Yeah, exactly.
Thank you.
Everything
Welcome.
in TensorFlow is defined first and then
execute
run
later.
on the graph.
I'm just trying to understand when we make cross that line. I wasn't sure if we'd done it yet.
Okay. So what we are going to do here is to just gather the required variables that we need to update when we are going to do our adversarial trainings. In particular, since we defined the discriminator under a variable scope called discriminator, using this method of TensorFlow, we can gather and get a Python list with all the variables used to define the discriminator. Everything under this scope is gathered inside these variables. The same for the generator. And we are going to define two training steps, one from the discriminator and one from for the generator, in which we are just going to use some standard optimizer. That's the optimizer, the object that will compute the gradient descent for us. And we are just going to say, okay, when we run in a session this node, the train D, you are going to minimize this D loss, updating this D vars list. And the same for the generator. As you can see, there are a lot of hyperparameters. For instance, I could have used another optimizer, another learning rate, another set of activation function, another architecture. Is art to understand how a model should be built to fit correctly your data. And this is the real part of the training. As you can see, we are just going to convert to a NumPy array the samples we generated on the first lines of this notebook. Then the something we need to do when work with TensorFlow on this low level is to initialize the variables. So right now, the variables of the models have random values inside. And yeah, I'm going to just create a directory GIFs, just in order to show you at the end of the training process and how the training process changed the output of the generator in order to fit our real data. So as you can see, this is our noise vector. We are going to use NumPy to generate a noise vector with mean 0 and a standard deviation of 1. And as a first step, we are going to train the discriminator. The discriminator, as you can see, invokes the train D and save in the D loss value variable the value computed for this training step of the loss of the discriminator. And as you can see in the feeddict, that's the way in which we create the mapping between a placeholder and real data. We're going to pass both the real input, because we are going in our loss, there are two terms, one that use real input, and also the input noise. The input noise is required by the generator, and so we have to pass it in this field in order to generate samples when the loss asks to TensorFlow to generate samples, because TensorFlow just do backtrack. So we run this node, and this node trigger the backtrack search on all the graphs, and all the graph of the generator requires input noise as input. So this is one training step for the discriminator. We do the same for the generator that need only its noise vector. And pretty much that's all. This will take a long time on this laptop, so you can run it if you want, or if you have opened it on Colab, just let it go in background. At the end of the training, you will find a folder called GIFs with a lot of images, and these images are just the output of the generator sampled over every 100 steps. And as you can see, this is pretty much what happens, and this is just, we are in the middle of the train. You can imagine at the input, the generator output is around 0. Right now, the distribution of the data is shifting around 10, because we have to consider that our target distribution is a distribution with the mean 10 and a standard deviation of 0.1. And as you can see, at this training step, I should have plotted, but there's no. We have learned how to move, how to shift the distribution around the mean value, but the variance is not right. So the training goes on until you will see that the generated samples are in the correct range, and so the learned distribution is exactly a normal distribution with a mean of 10 and a variance of 0.1. This will take a lot because there are a lot of training steps, and however, we can just talk about the next part. Right now, what we made until now is just model definition and model training. There are a lot of things we haven't do. In particular, our trained model is not saved anywhere. So just a wasted computation. We have not saved not the generator or the discriminator. We have not plotted anywhere in TensorBoard our summaries of our loss. We have not made any kind of data visualization, and there's no support for optimized input pipeline using the new API. And it's simply slow and with not so many functionalities. The TensorFlow developers recently created the estimator and the data API that are high-level API that for us allow to simply define just the model And once we defined the model and the input, we can just train, evaluate, export for serving, and make inference on our training models. So, as you can see, the distribution is pretty much the target distribution, so it's matching. Yeah. So before starting to have a look to the TF estimator API and the 2TF data API, there's some bonus exercise that if you want to do, you are free to just take this notebook and try to convert it to make this GAN conditional. As you can try to set the condition 0 in order to generate a normal distribution with mean 10 and a standard deviation of 0.1, and when the condition label is 1, you should be able to generate a normal distribution with mean 20 and a standard deviation of 0.2. You can just try to do this, but not right now because we are going out of time. And you can find the solution of this problem here. And for any issue, you can just open an issue on the GitHub page of this repo, and we will speak. So we can just go to have a look on the new API, estimator ntf.data. We can just go to the 2.2. And yeah.
Quick question. So the 100,000 loops, like how do you choose 100,000? Why not 1,000? How do you know?
This is another hyperparameter. So you have to try this, and then I have to visualize the data.
But there isn't some convergence measure you could use to break out if your iteration to iteration deltas are small enough? Or I'm just trying to understand why you wouldn't have some mechanism by which you could say, okay, good enough, break early.
Usually for any like GANs architecture, when you, for instance,
for instance, when you work with the images, there will be a point when your data set, the combination of your data set and your epochs will destroy your model, and you will see it when you have it on tensor board. It simply like explodes, and it starts like repeating a pattern. Basically, at that point, you have run out of epochs. So there is usually like a limit epochs that you can find, but it's all dependent on your data set. This is like the course of GANs, which is probably that there is no right way to do them, and there are a lot of papers that like suggest techniques and hyperparameters and stuff like that, but at the end of the day it all comes down to your specific use case, and you have to do a lot of tinkering and a lot of hyperparameter optimization on your own. So that is both the beauty and like the curse of the GAN. That there is no way to say that, for instance, like, I don't know, this is like a perfect number. The only thing which is pretty much consistent are the parameters that are fed to the Adam optimizer, in the sense that we usually always keep them the same because they are usually the best one. But once again, there is like, yes. It's really hard to measure the accuracy. Like in this case, since you have numerical data, you could easily do it, but more often than not, GANs are used with images, and with images it's really hard to have like a proper evaluation step. There are ways, and I will talk about them later, but they are real advanced, and more often than not they are really specific. For instance, if you're doing something like academics and then you're using some like public available data set, but maybe like your case that you are using your own private data set because it's like, I don't know, like proprietary data, and then you cannot use like rely upon normal metrics. There has been a paper which has been published like really recently, like if I remember correctly, like in the middle of August. So it was like around Ferragosto, from Ian Goodfellow, which is the father of the GANs, which proposed a way to rate GANs using an ELO system, Like you basically like let GAN fight in a tournament, and then you, upon giving the result of the tournament, you give them a score. But we have still to implement it, so we don't know how really it works. It was accepted at the ICLR, if I remember correctly, the conference, but we don't know how it works on practice. In practice, we simply like look at the generated output and we see if it's something like completely garbage or if it makes sense. It's usually actually really easy to like, if you're a human, to tell whether something is generated by a GAN or not, because you can see, and especially you can see the quality. If something is like trying to really fool you, then it's really okay. Otherwise, there is no way to see anything with the metrics.
Is the training of the discriminator and the generator independent of each other? Could you theoretically do it in separate graphs, compute graphs, or? Because the way I see it, the way I read it, it means that you basically first train the discriminator. One is done, you go on and you train the generator.
Yeah, but
I think one you run, like they do run at the same time, but like it's how do I say, like one and then the other.
yeah, but if you look carefully at the loss function, you can see that one is a function of the other.
Yeah.
So if when you trigger the generator loss, you are just going to use a defake, and defake is defined in order to have a G as input.
Okay.
And so you are triggered.
The comments about the basically hyperparameter tuning, does that also hold true for setting up the structure for the G and D networks?
Yes, also one other thing that varies is the architecture, but the architecture varies upon your data. And there has been like paper which basically like if you have a new model architecture, you find an acronym and then you put GAN on it, and then you have your own GAN. But at the end of the day, there have been like recently published a paper from Google Brain, which was a comparison between GANs. In this paper, apparently, like the architecture itself of the model, given like of course the same data set, is pretty much like a no factor. For instance, they match the deep convolutional GAN, which is the GAN that we will be showing you later on, to a model done with the ResNet block, and it achieved the same performance. And they are two completely different like architecture, even on the same data set. GAN is really like, it's more an art than a science. It's really hard to say what it works, and oftentimes you need like a lot of computational power just to figure things out. It's more like an engineering problem than a scientific and theoretical one.
Okay, so we can just go on with the other notebook. And this notebook is just an introduction to TF estimator and TF.data. And TF estimator, with respect to the plain old TensorFlow way of building a graph and define all the input pipeline and define even low-level things like I have to spawn a certain number of threads to generate the input. I have to take care of where to save my summaries. I have to take care of where to save my trained models. Thank you. TF estimator take care for us for a lot of things, and force us, that's the most important part in my opinion, to separate the input pipeline from the model definition. In this way we can define an input pipeline for any problem, for instance a classification problem, and reuse the same identical code in another problem, just like again. The most important namespace is tf.data, and the most important object here is the tf.data.dataset. The dataset object is something really cool that will generate an input pipeline that will spawn as much input queue as your hardware supports. It also adapts itself to any kind of hardware or network architecture. You can use tf.data to run the input pipeline on your laptop or on a Kubernetes cluster. It's the same code. So you can just try. If you have already downloaded this data set, we are ready to go. Otherwise, it would be a pain because it's heavy, really heavy. And with this Wi-Fi network is a little bit a problem. But of course, we can just have a look on how to define an input pipeline just for the train input images. And in this way, we are going to define a function that will return a closure that will be our function, our input pipeline function. And our function of the input pipeline must respect a certain signature. This signature is defined by the TF estimator API, and that's it. This is just a standard way to define the input pipelines. In this line of codes, you will see some closure that given an image string, so an image represented as an array of bytes, it converts back to a JPEG image, converts this image in 0 and 1, scales the values between -1 and 1, and resizes the input image to the size that you decide when you call the parent function. For instance, in this case, a default 64 times 64 times 3. Another closure will be this one. Given a path on our local file system, we just read this file as a binary string, and we invoke the other function in order to get a resized and meaningful image. And this is the closure we are going to return. We are going to use the dataset list files call that, given a pattern just like this one, it will just list every file that matches the pattern, and will create a list of files. So if the shuffle parameter, if you want to shuffle the input data, we can just apply other methods in this functional way, more or less. And then, yes, we can just go on. Once we have this data set of file names, we can map the function we defined above, the one that given a file name returns an image, and map this file, this function, to every file of the data set. In this way, this object is a data set of images right now. We can apply other functions like please create a batch of batch size, and if at the end of the batching process you have less than a batch size element, just throw away these elements, we don't need it. And some tuning optimization like prefetch some values before calling the other functions. And then the standard way is to just create a one-shot iterator that, given this dataset, creates an iterator over this dataset of batches and return the next element. That's pretty much the complete definition of an input pipeline that, given a pattern to match, we return an iterable inside the TensorFlow graph, not inside Python, but inside the TensorFlow graphs. This is an iterable object that our model will use to train itself. The estimator API also forces us to define the model in a specific way, but as you can just imagine, this is a problem because our estimator API wants just one model per time. But with GANs, we have two models that are working together. So, for instance, the discriminator definition, that's just like a standard classificator. We can just define it in this way. This is the architecture of DC GAN that, given features that we expect to be a batch size of 64 times 64 times 3 images, we just create this convolutional neural network. Have the linear output at the end exactly from the same reason of the other notebook. We can just define the loss, and we can just define any other thing we need to do to train, but we have to suppose that our labels vector will be a vector with both the labels 1 where the samples are real and the labels 0 where the samples are fake, stacked one on the other. And this is just a supposition because in practice we don't define networks in this way, because then putting the generator inside the estimator API will be pretty much painful. But we are lucky. We are lucky because the TensorFlow developers have created an estimator thought to work exactly with the TF data API and to train and evaluate and export for production GANs models. And this is the GAN estimator. And this is the part that Michele will talk you about.
Okay, hi everyone. Once again, I'm Michele, and I will show you the beauty of the GAN estimator, which is only one of the objects that are introduced in this amazing library from Google Brain, which is TF-GAN. Right now, TF-GAN is still in the contrib part of TensorFlow, which is the unstable, let's call it that, part of TensorFlow. So usually it is not used in production, but who cares? We move fast, we break things a lot, so we use it in production where at Zuru. So there is this cool factor. And during this time we got really acquainted with the library and how it works. And I'm going to show you how with this you can basically overcome the limitation of the traditional estimator API and define and run GANs like there was no tomorrow, because it's really easy. So the library itself is rather new. It was released on December 12 of last year. There is a blog post announcing it from the Google Cloud, the Google Brain people. It was made by Joel Shore, which is still the core maintainer. And once again, it's really sometimes the code can be quite messy when you go down to the level of how the library is implemented, but the advantages of the things it has are amazing. The most advantage, the most important one, the double network training. Basically, as we said, with the estimator, normally you cannot do two models together. Usually you have one model for one model FN. With this one, it's already built upon this the stuff that you need to do two models together to do a GAN. Otherwise, there is no GAN. The second one is that it gives you a lot of quality of life improvement. Basically, for instance, you have popular ready-to-use losses and penalties. You have summaries and evaluation steps that are already built in. The common evaluation are the inception score and the threshold distance, which are two different algorithms to see what the GAN does and evaluate. The only problem is that one uses the inception pitted against the a discriminator based on the inception architecture from Google, and the other calculate this threshold distance. But the limitation of these two algorithms are that are dataset dependent. So if you're not using something like the one we are gonna show you, the Celebe dataset, or I don't know, the CFAR 100, you will have problem using this in your pipeline. So once again, this is a limitation of the GAN, not the library. Then you have what we call the bag of tricks, which is an ensemble of techniques that have been shown to improve GANs training, hyperparameter architecture or choice of function that have been implemented in TensorFlow during these years, and you already have them under the hood, so you don't have to worry about them. There's also the library also comes with some examples of already pre-built model. There is the model that we are going to show you. It is not one of the that are very pre-built with it, but if you go online, especially we have left you all the links that you may need. You will find the models in the TensorFlow research models. There are models on CycleGAN, InfoGAN. They're pretty much the cutting edge stuff implemented right from the paper. Because this one is the library that Google Brain's researchers use internally to implement the GAN, or at least that's what they say. So, as I told you, the main benefit of this library is that it introduced like quite a plethora of low-level object. For instance, the GAN model that then it uses to build like some higher-level API, which is what we are gonna show you, which is the GAN estimator. But if you were to work with the GAN model, you will have to use a peculiar like structure of your training pipeline. You can find all information in the GitHub repo if you're more interested in the lower level. But the problem with the lower level, as with the normal TensorFlow, that it is harder to put them in production. Meaning that, for instance, if you have the estimator, when you have to switch between a vanilla estimator and I don't know, like a TPU estimator, because maybe you have like a freaking ton amount of images and you need to use a TPU, it's really easy to, basically they have the same API, and also estimator has the same API of the, a very similar API to the estimator in scikit-learn. So if you are comfortable like working with one, you basically like already know how to work with the other. It's really easy. And the other thing is that the estimator are right now the best way to put a model in production, because they have an API that is called a method, which is export save model. And when you do this method call, basically you obtain a graph which is optimized for prediction, and it is very easy to put it online, like on a Google Cloud ML Engine service, or I don't know, like SageMaker. I'm not sure how AWS support this model, but I know that if they have no support, support is coming, because it is like pretty much one of the standard way to put a model in production. So, more concretely, how does everything work? Well, it's basically what have you seen right now. So we can open the 3.2, which is all the 3.1, sorry, which is also the collab that I was mentioning at the beginning of the talk. Here it is the same, but with more theory, like covering the architecture of the DC GAN. So we do our import, we do the import LTF GAN like that, which is really not Pythonic, and I hate it, but that's the way they do it. So I don't personally like it, but that's how they roll with it. So the architecture that I will be showing you is the DC GAN, which is the deep convolutional generative adversarial GAN, which is just one of the many type of like architecture that you can use. Right now this is considered like the vanilla way to build a GAN, and it is one of the most stable one in relation to the training and its gradient, so it doesn't explode or do like funny stuff. There is like a huge amount of different GAN, as I told you. Basically, if you find yourself like do some changes to the architecture, give it an acronym, and then slap on it the GAN board at the end. Here you go, you have like an IPS-worthy paper. So there are like a ton. But we like to keep it simple, because at the end there has been like research showing that there are really no difference in performance between architecture. It all depends on your data set. So you basically have to try them out and find the one that suits you. The only peculiar things about this is that it is like fully convoluted in a sense architecture, meaning that we start from the noise on the side, on the generator. We apply like 4 or 5 the convolution, which is like the inverse operation of a convolution. And at the end, we obtain like the images. For instance, we are working with 64 by 64 by 3 images. So that's what we want to obtain in the end. Once we have these images, we feed it back to the discriminator. We apply traditional convolution until we obtain like basically like just one node, one neuron, which says to us, is it true, is it fake? Okay. There are, aside from the simple architecture, there have been like some changes and best practice proposed by Alec Redford, which legends say he is like able to discern even like the best of GANs, their output. He's never been fooled by any type of GAN. That's what the legend says. He's like a legendary researcher in the field. Like among the various modification from the baseline GAN, which was the one proposed by Goodfella, there has been this one, which is the all pooling layers are replaced with the stranded convolution and fractional style convolution for the generator. We use batch norm, like once again, batch norm is like its own kind of worms. There's people who say it doesn't work, people say it works, but not for the normal kind of reason. There's also people who say it actually like penalize the performance. Once again, your mileage may vary. It's really hard to say with the GANs, because there've been like paper who says I, and the paper who says not I, and paper who says completely like random stuff like D. So we also remove any fully connected layers. We are just using convolution because we want to like very deep architecture, so we can go pretty deep, except for the discriminator output, of course, because we need to squash everything down. We use ReLU activation and LeRU for the discriminator. The only thing we changes is the generator output, which is a 10H. Once again, these are like all hyperparameters. These are the one we found out that they works and they are consistent with the paper. Once again, your mileage may vary.
Can you say anything about intuition about why there's 4 layers?
Not really. I mean, it's probably like due to the dimension of the output. But once again, it's like we tried with some kind of data set that you can manage to like squashing it 5. We are replicating the original paper, which used the LSUN dataset, the one with the room, and it used like 64 by 64 by 3 images with a batch size of 128, and we will be doing the same thing. So we are sure that like, we need to establish like a baseline in order to see the changes. But once again, your mileage really may vary. There are like a lot of steps, some which are being like published recently. We briefly mentioned them. For instance, the CordConv, which is something out of Uber, which is a new way to do convolution using like coordinates. There is also spectral normalization instead of the batch normalization, which is another way to do like regularization between the layers. Apparently, spectral normalization should be the way to go, meaning that you are probably gonna want to check it out because it's really cool, but it's really hard. It's really math heavy and really hard to implement. There is like already an implementation out of Google, but we will not cover it in this talk because it's like something from published in April, while the architecture we are using is from 2015, if I remember correctly. So it's old in GAN terminology. The noise, as I told you, is what bridge you from the noise to insight, because we take the noise as input and we wanna like recreate an images. These are all the operation. As you can see, they're probably 4 because it's really nice. You know, you go 4, 8, 16, 32, and then 64 at the output. The only thing is that here we, in this layer, as we see in the code, we simply squash like the last channel because we want to have it like on RGB. We use this operation, which is the convolution. As I told you, it is already implemented in vanilla TensorFlow, and it's called convolutional transpose convolution. However, there was a paper from always Google Brain that they have published the result on Distill, which I really want to like mention to you as a cool way to see some how like paper should be done on machine learning. And they found out that using normal deconvolution, basically like using convolution transpose, there were problems like with the checkboard artifacts in the generated images. So they proposed a new way to do it, which is do not use the default convolution transpose convolution, but use a normal convolution with a layer of resize using bilinear or nearest neighbor interpolation. We are going to use nearest neighbor interpolation because in our use case has the best performance. Usually is almost always beats linear interpolation, so you want to check it out first before you check out bilinear interpolation. So we define this like layer to simplify things later on, and it is simply like we take the shape of our input, so we know how to resize it. We resize it, basically we double its dimension using the nearest neighbor algorithm, which is this one. Then we pad it, so we remove also boundary artifacts, which are once again a problem with convolutional neural network. These are like things that you find out when you run a lot of them. You start to know why you have like some strange problem. And then we do our convolution. So this is our deconv layer. Then we have the batch normalization. We could define our own, but there is a nice one implemented in TensorFlow layer, so we are simply gonna use it. So this is how we do the generator. As you see, it takes like an input and a mode. Mode is specific to the estimator API and especially the GAN estimator. It's the way you access these mode keys, which basically lets you specify things. For instance, if you want some operation to be run under the train and not under the predict, when we call prediction, we can do it by accessing this mode parameter. Usually, for instance, what we do is, let's say that we generate stuff at the end of the generator. We have an image. If we do like this one, if you check if the mode is predict, and then we maybe want to apply like some I don't know, like how can I say, like some post-process stuff, like on the image that we generate, but we want to do it only when we are calling prediction. Then we can access these mode keys to check it out and apply the operation only when we want to. As I told you, it is really simple. It's just at the beginning we take the input vector noise, we reshape it, we have this activation. Once we have reshaped it, which is basically the first step that you saw in this image, this is we do like this projection and reshape. Once we have this, we can start applying the various deconvolution, and before each convolution, we apply the batch normalization. So as you see, we go until the end, and the last one, it is the only one which has some peculiar, like as you see, it is different from the other because it is not a deconvolution, but it is a normal convolution because we want to squish all the various filters down to 3, because I told you this is how we obtain the last dimension. So we now have a 64 by 64 by 3. We take it, we feed it to the optimization, to the activation functions, which is 10H. As I told you, 10H was empirically shown to be like really like the best performance here. But once again, your mileage may vary. We have the output discriminator is pretty much the generator on reverse. Instead of doing the convolution, we are doing like normal convolution. And at the end, instead of having this one, this last convolution, we have the dense, the fully connected layer where we squeeze all the output down to just one neuron, because we remember that discriminator just want to discriminate between fake and real. So for the discriminator, we are going to use the custom conv2t, which is simply like a nice way to have a normal convolution neural network with convolutional layer, sorry, with like already initialized parameters. Since we don't want to repeat code, we are lazy and we use this one. As you can see here, there is this parameter, which is the conditioning, which is also what Paolo called labels. When you work with GAN estimator always expect your GAN to have some sort of conditioning, because it's already built to work with the conditional GAN. If you don't use any kind of conditioning, don't worry, just put something in here and don't care about it. Just for instance, you can put the underscore. It simply wants you to have these arguments in your model FN. Otherwise, it's like it go nuts on you and it destroy your work. It basically like throw you an exception. But you don't want it to go nuts on you, so you use the conditioning. And then you have your third parameter, which is once again the mode parameter, which acts as I told you, as a way to access the moment of the train, whether we are the moment of your like your workflow, whether you are in a training process or you are, for instance, in a prediction or evaluate and stuff like that. So as Paolo showed you earlier, this is like a very simple architecture. In order to not have like the typo, as you see, we always define the same net. This is just like something you can do in your code to simplify things up. And every time we do is always like except for the first, then it's always like a batch norm with a convolution, a batch norm with a convolution, until we can finally squash it in our to our last neuron. So, and then we have the output. Then we have a loss. However, in this case, as I told you, TF GAN. Okay, yeah, 2 questions, I think. Okay, sorry, yeah, just one. Yes.
But you're still overwriting your net in the beginning of your definition of the net.
Yeah, it's also like when you define it like that, you always get like we have this one, which is okay, yes, okay, it's always the same typo.
Yeah, exactly. Like this is a typo. It's a typo. Yeah, this one should be net. Yeah, it's the problem when you have to have always repeat the same. Yeah, copy and paste. Because if you like, for instance, give you, I don't know, like N1, N2, N3, and then you want to add something in the middle, you have like to rename everything down. It's a pain in the ass, basically. Yes. Yes, you can debug it easily using the TensorBoard. Once you basically like compile down the graph, you can like open the TensorBoard, and TensorBoard has like the graph analyzer, which basically show you each operation, and they are grouped under, like, for instance, like a scope. If you click on the scope, it opens up, and then you can see like each little operation you can open up until like the very basic primitive of TensorFlow. It's really easy to debug it. With that, there's also the TensorBoard debugger, which is another like stuff from always that help you in this kind of situation. Usually, you don't even like notice. For instance, with this network, we obtain like crazy performance on syllabus. So, as I told you, most of the stuff is hyperparameter. Maybe tuning it out doesn't really like change anything for you in the end. So at the what I was showing you is that we have the loss function, and here we don't need to define it ourselves. So we don't do any typo. As I told you, TF-GAN gives like some loss function out of the box. So we simply use them. You will see here, if you use the normal min-max and this way. This one is the one that's saturate, so we don't want to use this. But I'm going to show you this one here, and later in the code it will be the other one. Sorry. Okay, this is the saturating one, and we don't want to use it, but this is like to show you the simple API of TF-GAN. You have already like a bunch of losses, and you can even define your own to work like with them. It's really not funny to define your own losses, because it's really verbose in a way, but it's not hard. It's simply like boring. Then we have the practice, or how we give you the input function. The input function is, as Paolo told you, usually tends to follow this structure, even for both the normal estimator and the GAN estimator. And this is simply a closure. The parent function takes some parameters, and with these parameters we initialize the function inside it. Usually you return just the input. Here we have two inputs, which is noise and images. Noise, of course, will be the noise vector for the generator, and images will be the images for the discriminator. If you have like a conditional GAN, then you have also to specify the labels. Here we adapt the input function we defined in the previous notebook to work with the GAN estimator. We basically don't do anything. Okay, so as you see, the only crucial thing to know is that in order to streamline the training process so that we don't have to specify like a number of steps, we simply repeat the where is this? It's down here. We repeat the data set. We call this operation, which is dataset dot repeat num of epochs. And what it does is simply actually like repeat our data set for the number of epochs, and when since it is an iterable, when we run out of the data set, the train will stop. This is a nice way to basically like put an end to your training. In the end, we return the input fn. This is a parameter. This parameter simply is that as we sometimes may use labels. And if it was like using labels, then we won't need to have just the first parameter. In this case, there is no need for it, but it doesn't like hurt you. Then we define the closure I told you earlier. As you see, we give it like what is like the file pattern, which is where we are gonna fetch the image from, and then the hyperparameters. You most likely always want to keep your noise dims at 100. We tried by varying it, and we got like funny result. So keep it 100. There's always 100 in each implementation I've seen of the GANs. I've never seen anything like, for instance, I don't know, like 200. Don't ask me why. It's just once again another hyperparameter. Yes, we have the closure. As you see, we return noise and real data. We are not doing anything like with conditioning, so we don't need labels and stuff like that. Usually, when running production, we like to keep our hyperparameter in a separate file and not code them into our Python code. We usually read them from a TOML file, because it's really nice and doesn't have any of the problem with the YAML when you use it in production.